Hello everybody, my name is Rueen Fiez, and today I'll be walking through our machine learning solution as part of our University of Toronto Machine Learning 3253 final term project. Now, as part of our final project, we decided to go with a Kaggle hosted competition, and this Kaggle hosted competition is called the Predicting Molecular Properties competition. And Kaggle has a bunch of different competitions available and open to everybody. So we just happened to go with this particular one because we have an interest in atoms and molecules, and we thought it'd be cool. So what is this competition about? Well, this competition is hosted by members of 4 different universities mentioned here, and they're doing work in the area of nuclear magnetic resonance, or NMR. And what NMR is it allows researchers to dive deep into a molecule structure and dynamics and interactions, and it allows them to make advances in the areas of pharmaceuticals and material science and so forth. So this specific competition is asking machine learning enthusiasts to create an algorithm which can predict the interaction between a pair of atoms. Now, this value is otherwise known as the scalar coupling constant. Now, Kaggle tends to provide data as part of all its competitions, so we can take a look and see what we're working with here. So when you open the training file, you can instantly see that there's a bunch of molecules. Each molecule has an atom and two atom indexes because we're providing a prediction for a pair of atoms. And we have the associated Y target for each atom there as well. So that's great. We're also provided with a similar file for testing, as well as a structures file. And the structures file shows us specifically what the Cartesian coordinates are for each atom in a molecule. So you can essentially take these values, put them into a space, and visualize this molecule and see how it looks if you really wanted to. Now, the structures file is important because a lot of the features in the feature engineering that you'll see in a second has to do with the atom's position, its position relative to other atoms and molecules, and so forth. So, sorry, not other molecules, other atoms. So, why don't we take a look at how the training data is distributed for us for the Y target? So, that scalar coupling constant that we discussed earlier, here's the distribution, and as you can see, it has a bimodal distribution. A lot of the values are focused in the 0 range area. However, there are some that go into the negatives, and we also have some instances that go above 100, even touching 200. So that's good to know. Now, Kaggle's training data and test data is a good start. However, we noticed that the test file that Kaggle provides us is missing some features that is provided in our training file. Now, why is that important? Well, remember how we have the scalar coupling constant here? Well, this value is actually made up of the value of 4 different other features. And for the training, we are provided with the values for these 4 other features. However, in the test file, we are not provided with this. So that makes it a little bit challenging in that these features we believe are highly correlated to our Y target, and I'll show you what I mean by that. So if this was our Y targets distribution, the distribution of the 4 missing features, which you saw these names earlier, FC, SD, PSO, and DSO, which are these guys right here, well, these kind of look a lot similar to the Y target distribution, the scalar coupling, don't they? So we felt that, and this drove our model development strategy, we felt that we'd have to predict these missing features first before we can accurately predict for the Y target scalar coupling constant. So that's basically what drove our model development strategy. And what we want to do is, before we jump into what we did for the model development, we want to touch on some of the pre-processing feature engineering work that went into this. So as far as pre-processing goes, we kept it simple. There wasn't much need to clean it up too much because all we really needed to focus on was we had some infinity values as part of our training data, and what we did with that is we turned them into NANs, and then we used a simple imputer in our pipeline here to turn the NANs um, into an actual value. We also used a standard scaler. We threw it all into a pipeline, and we used this pipeline to do our data transformations as we go along. So that's basically the feature engineering. And the only other thing I wanted to touch on was that we did try and implement dimensionality reduction. However, we saw that there's no material difference in our score. So we kind of put dimensionality reduction to the side right now, and it would take some further research to see what type of strategy would use, whether we should use PCA, KPCA, and what threshold and what not. So part of our conclusions a little bit later on further study. So as part of our feature engineering, like I mentioned earlier, the way these atoms are positioned relative to each other are part of the features that we're collecting to make our prediction on the Y target. So we have a bunch of different mean distances, max distances, and we kind of collect all this and we throw it into a data frame, a pandas data frame, and we use that to fit our models. Now, that's a good segue into our model development here. So, like I said earlier, we want to predict on the 4 missing features. We want to add those 4 missing features values to our test file provided by Kaggle, and then we want to have our final model predict against this augmented test file, because we feel that augmenting the test file will give us a more accurate Y target value if we include these features in the test file. So we use random forests because we felt that ensemble models are some of the most powerful models and we want to see them in action. So we said, why not use it for this competition? So as part of the models used for the 4 missing features are all random forest regressors. Because this is not a classification exercise. So we create the models, and once we create the models for each one, we then predict for each one, and we add it to the test file. We actually also add it to our training file because we wanted the final model to be trained on the train file, which includes predictions for those 4 missing features. We then take the predictions from our final model and we basically export that into a Excel sheet called a submissions file. And then we take that submissions file here. So we have an ID and these are the predictions that we made for our project. And we submit that to Kaggle through the submission process here. Now I'm not going to actually do this right now. However, I wanted to just show you that we did place, and the way Kaggle evaluates for this particular challenge is that it uses the group, the log of the group MAE, mean absolute error, and it's the mean absolute error for each molecule type, and it gets the log for that, and we get a score basically. And so we did place 2,296 out of a possible 2,478 individuals and teams. So it's a start, but clearly our model needs some more refining and fine tuning, and which we'll do through grid searches for hyperparameters and some more exploration of how to pre-process the data. Our conclusions for this include increased feature engineering that we can include. We can do some more pre-processing using dimensionality reduction, and we can choose more powerful models through hyperparameter grid searches. So that's basically the end of our presentation here. So if you liked what you saw, please feel free to leave a comment. My name is Rueen Fiez, and bye for now.